Part of the reason that pulsars are relatively easy to detect is that they beam light towards us at remarkably regular intervals. For this reason, they are also seen as cosmic clocks, since they pulse in some of the most stable patterns in the universe. For a typical pulsar, it takes 317 million years for it to drop 1 second off of its period. Amphibians, as a class of animal, have existed on Earth for 315 million years, which means a pulsar somewhere has not dropped 1 second since amphibians have emerged as a type of animal. That's pretty stable. The only objects in the universe that pulse so regularly like this are pulsars, so when an astronomer sees something like this, they can be pretty certain that they're looking at a pulsar. Hence, they are relatively easy to detect. If you know a lot about space, then you might hear that pulsars barely change their rotation speed over time and think, wait, shouldn't they not change their rotation speed at all? They're in space, there's no air or air resistance to slow them down, nor should there be any other external force. This is correct. There's no external force that slows a pulsar down. Instead, this slowdown, or spin down as it is called, comes from within the pulsar itself. To explain exactly how pulsars slow down as they age, I've got a couple fun facts for you. 1. Pulsars have some of the strongest magnetic fields in the universe. 2. When a magnetic field rotates, or moves periodically at all, it radiates away some of its energy in the form of light. When pulsars rotate, they emit this same energy, and that energy is pulled from their rotational energy, because you can't just create energy, it's pulled from their rotation, thus slowing down the pulsar. However, this loss of energy is extremely slow, and in some cases it's not enough to stop pulsars from speeding up. Pulsars that speed up their rotation are, as you might imagine, the fastest in the universe. These pulsars are called millisecond pulsars, for their periods which are in the milliseconds. After hearing about these millisecond pulsars, I bet you're wondering what the fastest pulsar on record is. Well, I got you covered. It's pulsar J1748-2446, and it spins at 716 rotations per second. Could you picture an object the size of Manhattan rotating at 716 cycles per second? If it made a noise every time we got a pulse from it, it would sound like this. If that sounded like someone started running a blender next to your ear, that makes sense because it actually rotates faster than a kitchen blender. That should drive home the point of this pulsar is very, very fast. So how does a pulsar even get that fast? I'll give you a hint, it's not born that way. Instead, pulsars get that fast through what is called an accretion disk. What is an accretion disk? Well, when a super heavy object like a pulsar or a black hole gets close to an object like a cloud of gas or even a star, that heavy object, in this case a pulsar, will rip apart whatever is near it and cause its ripped apart remains to spiral inwards towards it. Eventually, the stuff spiraling inwards is going to hit the surface of the pulsar, and the momentum from that is going to cause the pulsar to speed up a little bit. This is the same concept as you flicking a fidget spinner to make it go faster, only on a much larger scale and over a much longer period of time. Eventually, this effect can cause pulsars to go from having periods in the seconds to having periods in the milliseconds, as was the case with pulsar J1748-2446. Pulsars, like most celestial bodies, are extremely far away from the Earth. The nearest pulsar to us is 250 to 1,000 light-years away, which those numbers are both vague and kind of underwhelming, especially when talking about objects as extreme as pulsars. So to put it in perspective, If someone decided to go back in time to the time of the Neanderthals, and they went back in time with their supersonic jet, which can also fly in space, it's the coolest jet ever invented. They go back in time with their supersonic jet, and they start to fly towards the nearest pulsar in the time of the Neanderthals. They would be arriving at that pulsar about now. That means it would take the entirety of human development, 130,000 years or so, for someone going in the fastest vehicle ever invented to reach a pulsar, any pulsar, the minimum distance to a pulsar. They'd be reaching it about now. And also, just to harken back to an earlier point, in the time it would take that person in that supersonic jet to reach that pulsar, that 130,000 years, that pulsar would not have lost more than a few milliseconds off of its period.